Friends, back to you once again with tutorial 9. We are now entering into a little complicated and difficult exercise. Difficult, but for a very simple interconnected network. So we have yet seen only radial system in which source is only on one side and load on the other. Parallel feeders also source on one side and load is on the other side. That's all what we have seen. Right. Now we are taking source on both sides, and on all the buses those are concerned, there will be loads. So there will be many relays, and how to coordinate the relay settings in such case. How to coordinate how to grade the relays so that the relays operate as fast as possible, and yet the adequate protection is given to all equipment, transmission line, transformers, this, that, etc. of the power system network. And that is going to be little difficult exercise. Usually this I have not been teaching in BVM engineering college also, because it would become difficult. But when I have come to teach you the complete power system protection, I think I should take at least a very simple interconnected network. So my friends, we are entering into that. Yes, friends, then this is our network. You can see a very simple network. There are only two buses. You see, if you talk of Gujarat state, then I think there must be at least 50 buses. There are buses of 765 kV, there are buses of 400 kV, there are buses of 220 kV, there are buses of 132 kV. At least up to 132 kV is into interconnected network. Well, 66 kV, 11 kV may be radial system as we have talked about, and therefore the tutorials which we talked about are not wrong, are not in vain. All 66 kV, 11 kV are radial system or maybe parallel system. So the setting exercise is all right, correct. What we have done is not wrong, that is required. But then when we enter into an interconnected system, then also you will have to set the relays. No doubt, as we will be talking further, 132 kV and further, the main or primary protection is distance protection, but yet at the backup, overcurrent and earth fault is there, and therefore you will have to decide the settings of them, and while deciding you will have to coordinate them. Now how to coordinate is a little difficult exercise, so we are entering into that. So to explain the network, I've got only two buses and two lines. Very simple, right? On one side, I've got three generators, 15.75 kV, 210 megawatt, three generators, right? Connected to GTs to 50 MVA. On another side, on bus B, my friends, I've got these generators to 50 MVA GTs and same 15.75 kV, 210 megawatt, but two generators. Say, for example, this is just I'm taking one kind of system which is typical, not impossible. You see, such systems are met with, or rather even more complicated systems are met with in field practices. I've got load on bus A, 200 megawatt and 150 megawatt, total 350 megawatt of load at 0.85 PF flag. And on the another bus B, I've got 300 plus 300, that is 600 megawatt load at 0.85 PF. I'm not talking about generator relays now because I'm talking about transmission line. So right now I'm talking about only four relays. So just think a very simple system, two buses, two transmission lines and four relays, and you will see how complicated the exercise is going to be, right? So obviously when fault occurs, the fault will be fed by generators at both ends. That is very obvious. That is very obvious. I have got on right side CT is 1500 bar 1. R1 and R2 relays are being fed by the secondaries of CT 1500 bar 1. R3 and R4 other relays on side B. Yes, right. R3 and R4. These relays are fed by 1000 bar 1 CTs, and all four relays are obviously directional with the direction as shown away from the bus, operative direction away from the bus, right? So that is how the system is. Now you see, because the whole both the feeders are identical, whatever is the setting of R1, same is going to be of R2. So I have not to find out both. If I find out R1, R2 is same. Similarly, if I find out R3, R1 and R3 are not same. You see, you just try to see because generators on another sides are different. CT ratio is also different. But R3 and R4 are identical. Whatever is R3 is R4. So actually speaking, I have to find out the setting of only two relays, R1 and R4. So R2 and R3 are done. But to find out the settings of R1 and R4 itself is going to be how long? You see, I want to limit the video to 30 minutes, but I think I will not be able to because the exercise is little difficult, little complicated. And we would want to enter into complicacy. I was telling that I will enter into complicacy because I want to teach to you power system protection in as much details as possible, because our system is like that. Our system in Gujarat, our system not in Gujarat. Gujarat is connected in western region grid in which there are 5 states: Gujarat, Rajasthan, Maharashtra, Madhya Pradesh, and Chhattisgarh, right? So there are similarly there is southern grid. Similarly there is eastern grid. Similarly there is northern grid. Similarly there is northeastern grid, and all those grids are now combined, and national grid is existing in India. You see how difficult and how complicated the exercise will be. Let me tell you that the exercise cannot be done manually as we are trying to do in this example. Manual means using our simple calculator, scientific calculator. You just cannot do. You will have to prepare, you will have to enter into some algorithm. Many researchers, many PhD students have done PhDs. They have prepared algorithms. What they are doing? What all they are doing is they are trying to they are trying to coordinate the relay, and they are trying to optimize the relay setting. Optimize the relay setting means the relay should operate as fast as possible and yet as selective as possible. And let me tell you, friends, that as on date, it is not possible. No one has ever been able to do that. That means if say one relay is there, the fault occurs near that one relay, near that one bus, then there are some 11 relays backing up. So there are certain fault locations in which case neither the primary relay operates nor the backup relay operates, and some third relay which is not at all connected with it, which is no concern, that operates. And that is being known as, in technical language, sympathy trip. That sympathy trip occurs. So the goal of the researchers is to reduce the sympathy trip. As far as I remember, I don't know that I am a very big person, worldly person. I mean, worldly known person in power system protection, that I don't know. I cannot tell because Professor Phadke is Bhishma Pitamaha of this Arun Phadke is Bhishma Pitamaha of power system protection. Probably you have to ask him. But as far as I remember, yet one sympathy trip must be there. So some researcher have found out that in my system I have 4 sympathy trip. Second researcher says that my algorithm gives me 3, so is better. Some third will say that my research gives me 2, that is yet better. So sympathy trip is reduced, but sympathy trip is not gone. I do not mean that protection is not occurring, because basic protection is given by distance protection. Distance protection works well. and therefore there is no question of wrong or maltripping. But if distance protection fails, then overcurrent earth fault will certainly give certain maloperations in certain cases. I mean, that probability is negligible, maybe, but that probability is there in interconnected system. That does happen in any interconnected system. Sympathy trip is always occurring, right? So that is, people cannot do without it. And yet, you see, while doing that, you see, I have got some 50 transmission lines inside Gujarat state. So how will you do it? All 50 transmission lines are. Forget about generators. I am not talking about the contingency of the generator, that is stripping of one or two generators here or there. That I am not talking. I am just talking of transmission lines. There are 50 transmission lines. If I consider one line contingency, means I will have to do 51 calculations. That means all lines are working. Line number 1 is not working, then power flow analysis is different. Line number 2 is not working, power flow analysis is different. Line number 3, so 50 such possibilities, and all lines working means 51. I am talking about one line contingencies. My dear friends, yet on date, all researchers have considered one line contingency. If some viewer, if some reader will tell me that some researcher has worked on two line contingencies, means very difficult. Try to understand. 50 transmission line, two line contingency means all 50 lines working. Then line number 1 and 2 is not working. Then line number 2 and 3 is not working. Then line number 3 and 4 are off. You see, very difficult. Two line contingency, three line contingency, no one have worked. So the problem is very complicated, very difficult, very cumbersome. And my dear friends, that is the very important reasons why people have shifted to distance protection from overcurrent and earth fault protection. That is what I would want to hint here at this particular instant. Yes, friends. So leaving aside this, I go ahead. The details are like this. Relays R1 to R4 are directional normal inverse overcurrent relays wired for 3 overcurrent and 1 earth fault scheme. Overcurrent units usual 50 to 200%. Ground relays usual 10 to 40%. 7 equal steps. Loads are shown in the figure. Fault currents are tabulated for F1 and F2. Try to understand. When fault occurs at F1, maximum current will flow through relay R1. Try to understand. In CT1, 1500/1, CT1 maximum current will flow, because current will come from left hand side generators also, and the current will come from right hand side generators also. Right? Obviously, very obviously, because right hand side generators means from bus B, from R3 to F1. There R1 is not in picture, but R4, R2, R1 and F1. If you consider that, you see that route is also there, and that route is giving you equal current, because F1 is just near bus of R1 relaying point. Therefore, through R1 maximum current will flow. R2, R3, R4 less current will flow. If fault occurs at R2, same thing will happen. Maximum current will flow through R2. If fault occurs near R3, on left hand side of R3, then same as F2. When fault occurs at F2, R4, then maximum current will flow through R4. Right? So these currents are given in this table. For F1, maximum current is flowing through R1 or CT1. Primary side current is given 6852. CT2, CT3, CT4. Less currents are, and same, obviously same, because that current will be same. F2 maximum current is 5539 amperes, C24, because F2 the generators are only 2, so current is less, but the other currents are more, because on left side the generators are higher capacity. 3 generators are there, so that is same 1910. LG faults we do not talk about right now, because that will be next tutorial. It would be difficult to cover so many things at a time, because this tutorial itself will not be limited to 30 minutes. Difficult, very difficult. because very, very difficult to convince people as to what is going to happen. So remember these things. We'll once again come back to these figures, right? So we don't talk about ground relays right now, overcurrent relays, operative directions shown, and we consider single line contingency. My dear friends, here single line contingency means nothing. Here single line contingency means two line contingency you cannot take. If two line contingency means everything gone. Generators are working on house load, nothing is there now. Because or the generators on left side will be able to feed load to whatever it can, because total load is 350 megawatt, whereas the capacity is quite large, 630 megawatt. So probably they will be able to feed their own load at bus A. At bus B, 600 megawatt load is there, but the generation is less. So obviously you will have to do some load shedding. So if two line contingency I take, there is no use of taking two line contingency here. If there are 50 lines, then well, you can think of two line contingency, which no people have done. You see, if some viewer, some reader is hearing me, and if he is going through the complete video, then because there are many people in my WhatsApp, they are telling that, sir, will you guide in research? So I always tell them that I am not a researcher. I am myself not a doctor. I am not PhD. I am not interested in research. I am a consultant. I can guide people in their industrial problems. I can guide students in their studies. I can teach them protection well. I am not a researcher, but I do give hint as to where you can do research. Two line contingency you can do. Here it's no question. One line contingency means one line will become off. That possibility we will take. Two lines will be on. That is quite possible. There is nothing wrong about it. But if one line becomes off, then it is going to be difficult. So we will consider one line contingency, my dear friend. And for that, we will have to do power flow analysis. You see, two line contingency also power flow analysis can be done, but then the current will be hard. In two lines, total current is flowing. So in one particular line, current will be hard. So that is not the worst case. Worst case for finding out flux setting is single line contingency. Only one line is working, either upper line, lower line. In our figure, that is left side line or right side line. So if you talk about single line contingency, I will talk about R1, R2. Say upper line is off and R2, or lower line is off and R1. So what will be the setting of R1? What will be the setting of R1? Maximum current that can flow in given direction. What is the maximum current that can flow? Either load, that is 300 plus 300, 600 megawatt, or generation, 210 into 3, that is 630. But it is also given, my dear friends, if you just see, it is also given that the 10% of power is being used. I think it was given somewhere that 10% of power is being consumed by the auxiliaries. It is not given, but you have to assume obviously that 10% of power will always be consumed by the auxiliaries, right? Auxiliaries will consume some power, because for running 210 megawatt, you have to run a boiler. Boiler means boiler feed pump, condensate extraction pump, CW pumps, right? The FD fan, PF fan, ID fan, and whatnot. Many things you have to run. So they need power. So out of 210 per unit, 21 megawatts are consumed in this. So 210 into 3 into 0.9, 10% I take out. So into 0.9, my dear friends. So 210 into 3 into 0.9, 567 megawatt. Whereas my load is 600 megawatt. 600 megawatt cannot be fed by 567. So my setting will depend on 567. Load is 600, but I can feed only 567. So I will not be able to feed 600 megawatt. That does not mean that 600 megawatt will not be fed. The remnant load will be fed from generator set and B. No problem. But from here for relay R1 only 567 megawatt will go. So current you can very obviously understand 567 10 raised to 3 for amperes, 100 for percentage, root 3 220 voltage 0.85 power factor, 1500 bar 1 is the CT ratio. So I am getting 116.70%. So R1 or R2 because both are identical. 125% is selected. Right. Similarly, R3, R4, my load is 350 megawatt. My generation is 378. Generation is more, but I don't need that much. It does not mean, I don't mean to say that remnant generation is going in vain. It is fed by, fed to the loads at bus B. But through R3, only load is flowing because generation, the generation is 200 plus 350, yes, 210 into this 420, but here my load is 350. So load is less. So load will decide the plug setting. So my plug setting for R3, R4 is decided based on 350 megawatt load. So that comes to 108.6. So that also comes to 125% because there the CT ratio is 1000. There the CT ratio is 1000. So I have arrived at plug setting R1, R2, R3, R4. And plug setting I can arrive at by conducting power flow analysis. Power flow analysis is very simple in this 2-bus system. But had there been 50-bus system, for different contingencies, say for 51 cases, you will have to run 51 times the power flow analysis. And for a particular relay, say R1 or R2, you will have to find out which is the maximum current that is flowing in that case, in the worst case, out of 51 probabilities. That is for one relay. And there are 50 lanes means 100 relays. So for 100 relays, you will have to do. I think you will understand that you will get an headache and you will have to take many paracetamols. So you have to run the program on some, no doubt, you have to prepare the algorithm. The person who is preparing the algorithm will have to know this, all these manual things. So these manual things are not useless. I am hearing the argument that now because the algorithms are available, people need not learn power system protection. Learn the algorithm and do everything. Matlab ki, the God will do everything. My grandfather, not my grandfather, my father-in-law was very much worried about the the labor that was required for preparing rotis, because girls, the women of the house will have to go to kanti, flour mill, get the flour, right? And then they have to prepare the thing for preparing the rotis. Then they have to small pieces they have to take. Then they have to prepare the rotis, and then they have to उसको पकानी पड़ेगी. They will do it on oven or on the gas. So he was thinking that there should be a machine that if you feed the gehu, wheat, then rotis will come out on the other end. Then I told him that then the automation would be yet better, that you feed the wheat. You feed the wheat. गेहूं करो और बाहर क्या निकलेगा? बाहर मल निकलेगा. Whatever you are extracting out, the extract which the person is extracting, that will be the best automation. Friends, that is not possible. Automation is not possible to that extent, and you will have to depend on certain manual things. The algorithms that are prepared, those who are preparing the algorithms, they are not computer persons, because computer persons do not know what is power system protection. So you need computer person, IT person will need a help of power system protection. One person will do, others will just follow. But I would want to ask you a question, whether you want to become a follower or a leader. If you want to become a leader, then you will have to understand how the algorithm is prepared. Because you see, if the system changes, then your algorithm will have to change. And then it will be very difficult for you to understand, because you are not knowing any fundamental. One student in MTech had prepared an algorithm, and he was defending his thesis in final viva. and he did defend everything. Then one person like me, an examiner, asked him, what is plug setting? What is plug setting multiplier? What is time multiplier setting? What do you understand by IDMT overcurrent relay? What do you understand by normal inverse? Very inverse. Oh, sir, sorry, I know only algorithm. So then what for you are an electrical engineer? So my friends, you will have to learn this thing. So we are right now learning for a very simple system. R1, R2, 125%, R3, R4, 125% plug setting is done based on power flow analysis, considering the worst possibility out of line contingencies. So going to next, for time multiplier setting, you will have to go for fault current analysis. Fault current analysis means if there are 50 buses in the system, find out the fault current for all 50 buses. That means current flowing through all the lines, fault current flowing through all the lines for a fault on one particular bus with all lines working. Then same fault location, one line contingency means line number one contingency. Same fault location, line number two contingency, yet one line contingency. Line number two is different. Line number three, very difficult, very cumbersome. But here, my dear friends, we are having only two lines and one line contingency means very simple. So fault current calculations are not very difficult. I did it manually. I have done it manually, right? So for both the buses, I have found out for both the buses, obviously. This is what I've done. F1 means on bus A and F2 means on bus B. Because nearer to bus A is bus A only, no? Just after breaker at A means it is bus A only. Means I have done it A and B both, F1 and F2. And I have found out the fault currents manually by simple calculator. This is what I have done. I have myself done. Yes, I have prepared an example myself. This is not any, but this is possible. Such a system is possible. So fault current analysis you will have to do for all the possible contingencies, and that I have done. And based on that, now I am finding out time setting, my dear friend. Fault plug settings I have done. So, but before I find out the time settings, I will have to, this is what I have done. Plug settings I have done, right? R1, R2, R3 that I have done. Then I have to go for plug settings. But fault current calculation and then primary backup pairs. That is very important. Primary backup pairs is very important. So now if there are 50 buses and 100 relays, then one relay may be backed up by some 10 relays or 11 relays. I don't know. But here primary back and for that primary backup pair also you will have to prepare a algorithm, right? Well-known algorithms are available. One professor at IIT Roorkee has developed an algorithm. It is a 3-vector algorithm, right? If I mistake not, node, far, and next. There are some 3 nodes, and it is a link net structure. Based on link net structure, you can define a system into computer, and you can also find out the primary backup pairs. Means if R1 is a primary relay, say for fault at F1, I know that R1 should operate primarily. R3 also should operate primarily, both relays. If R1 fails, then which relay will back up? I'm not going to generator side right now. Try to understand. I'm talking only about line. Generator, I'm yet not talking. That exercise will become yet complicated. So I do not want to enter into complicacy on the first go. This itself is quite a lot much of complicacy. I probably find that if 100 viewers will go through the complete video, I doubt whether 50 will understand, because my student friends are not understanding. Wherever I have taught, Nirma University, the best in Gujarat state, PDPU, now known as PDU, Pandit Dindayal Energy University, where I'm going as visiting faculty, BVM, where I worked for 26 long years, and I've gone into many colleges. People are finding protection very difficult. There are very few expert persons in protection in Gujarat state and probably in India as a whole. I don't mean I'm alone. but there are people who can be calculated on fingers. So people will find it difficult. But then, you see, let us try to understand that if the fault occurs at F1, R1 should primarily operate. R2 will not give backup because the fault current is flowing. Kaise fault current flow hai? Fault current is flowing from bus B, that is from generators there, R4, R2, R1 and F1. So for R2, the direction is non-operative. So R2 is not going to operate. R4 is going to give backup. So R1 should operate first and R4 should operate later. We are taking 0.25 second as discriminating time interval. So R4 should operate by 0.25 second more. If it is 0.3, I don't mind. 0.35, I don't mind. But not less than 0.25. Try to understand. So for that, I am carrying out an exercise. So first, primary backup pairs. So R4 gives backup to R1. R3 gives backup to R2. But most astonishingly, most surprisingly, and most difficult to understand is if fault occurs at F2, then R4 will operate first and R1 will give backup. So R4 gives backup to R1 and R1 gives backup to R4. R1 and R4 give backup to each other. R2 and R3 give backup to each other. That becomes a very complicated exercise. So my dear friends, this is my primary backup pairs for 4 relays. Very simple to understand. For 50 lines and 100 relays, you will have to rather depend on certain computer algorithm to find out primary and backup pairs. So here I have found out primary backup pairs. There are 4 primary backup pairs. So going further, time settings, plug settings, I have already done, right? Calculation of time setting of phase relays. As there is no last relay. Now, you see, in earlier case in radial system, we were starting from last relay near load. Now, there is no load, there is no last relay. It's a circular system. So, at random, I will have to start from one relay. So, I start with R1. My dear friends, I start with R1. I start with R1. I start with R1. You see this network, I am starting. Anyway, I can start with R3 also, no problem. But I am starting with R1. I take fault at F1. I find out time of operation of R1. For that, I will assume TMS of R1 as 0.1. You can assume 0.05 also, I don't mind. Whatever you want to assume. I am assuming 0.1. R4 should operate 0.25 second later. And once I found out TMS of R1 0.1, R2 is also 0.1. And when I have found out TMS of R4, whatever 0.15, 0.2, that is same as R3. So you will find that the thing is quite simple. But friends, not that simple. Not that simple. Not that very simple. So my problem starts here. That after deciding primary backup pairs, as there is no last relay, I go for R1. What is PSM of R1? The fault current is 6852. I go back. Fault current for R1 is 6852. Check up. Fault current for CT1 6852. For all others 1410. Try to remember 6852. So for 6852, PSM of R1 is 6852 upon 1.25 because 125% of 1500 CT ratio. 0.4 because the relays are voltage controlled over current relays. I will have to use the relays as voltage controlled over current relays because it is a must. I have to use voltage control because otherwise my PSM here, well, for R1 it's okay, but for R2, R3, R4, PSM may be less than 1 or maybe very nearer to 1. So relays will not at all operate, you see. So voltage control feature because of which the plug setting automatically reduces to 40% of its set value. When fault occurs, when there is no fault, your plug setting is normal. So under load conditions, the relay will not maloperate. That is a very, I mean, it's a magic of the voltage control feature, right? And that voltage control feature is not a magic. That was possible in the era of electromechanical relays also. That was possible in the era of static relays also, and that is very possible, very easily possible in numerical relays also. You see, if time permits, someday we will talk about it as to how that can be done in numerical relays. And if time does not permit, then if you have any questions, because after hearing my videos, there are at least 10 to 15 student friends whom I am not knowing also. One friend, Mr. Adam, he must be hearing this, he will hear this video. He is from Malaysia and is posing many questions to me. I am not charging anything. There is one person in JK Lakshmi Cement at Udaipur. He is also asking many questions. Uh, there are people in different parts of the world. They are asking questions to me. They do refer me for many of their questions. There are many researchers who would want my help for research. Even if I tell that I'm not good at research, they tell that, sir, we will, so however we will take one Google Meet and we will discuss. Something will come out of that. Maybe something may come out. So 9.136 is the PSM of R1. Top of R1, time of operation of R1, 3 upon log 9.136 into 0.1 I have assumed. That means I have started with the lowest TMS. You can assume 0.05 also. 0.025 and 0.0125 also people are assuming. You see, because nowadays the dial in electromechanical relays is so big that you can take parts in electromechanical world also. In numerical world, it is quite very easily possible, because it is only digit that you have to write on the display panel. It becomes very difficult. I mean, very easy to decide the TMS, lowest TMS that you want to decide. Right now, I am starting with 0.1, so 0.3123 second. Therefore, time of operation of R4, the backup relay, is 0.25 more, 0.5623 second. What is the PSM of R4? Because there, for the same fault location F1, current is not same here. You see, in earlier case, radial system, current used to be same. Here, current is not same. Current is different. Same fault location, current is 1410. Same, the voltage controlled relay. My flux setting multiplier is 2.82. You just see, if I would not have used 0.4, then this would have been less than 1. Then that relay would not at all have operated. That would be wrong. Therefore, voltage controlled feature is a must. The TMS of R4, therefore, is 0.5623, which is the required time of operation, and 0.084 means the next available 0.1 I am selecting. That means TMS of R1 I had started with assumption 0.1. TMS of R4 I am calculating 0.1. Therefore, it seems, my dear friends, once again going back to this figure, R1 I assumed 0.1, R4 with proper discrimination margin I have calculated 0.1. R1 and R2 are same, so R2 is also 0.1. R4 and R3 are same, R3 is also 0.1. Plug setting R1, R2 is 125%. Plug setting R3, R4 is 125%. R1 and R2 time multiplier setting is 0.1. R3, R4 time multiplier setting is 0.1. It seems that our exercise is complete. No, my dear friends, incomplete, because I have considered only fault location F1. I have to consider fault location F2 also. Here, in this case, only 2 fault locations. Had there been 50 lines, I would have to consider 50 locations. And yet, in all those 50 locations with one line contingency, the time discrimination margin 0.25 second has to be satisfied. If not, then you have to go for reiteration, second iteration, third iteration, fourth iteration. Iterative exercise you have to do, which is very cumbersome. So I once again come back to you, my friends. Therefore, distance protection is better in an interconnected system. And therefore, in the next tutorials, we'll start talking about distance protection system. And distance protection system has also many problems. And therefore, the best protection system in the world of protection, is differential protection. Line differential is the best protection system. And even in that, there are going to be problems. And because there are problems, engineers are required. If there would have no problems, or if there are problems which are known, that there are 100 problems and the solution is known, then no engineer would be required. Some laborer would sit and would do, because we would be told that problem number 1, solution number 1, problem number 2, solution number 2. But unfortunately, problem number 1, solution is not known. You don't know the solution. You have no solution. You will have to find out solution. That is where the engineer is required. So here what you will have to do, I will have to create, I will have to think of a fault at F2, find out time of operation R4, and see time of operation of R4. Now I cannot assume anything. Plug setting is 125% and TMS 0.1 I have already calculated. And then for that fault current R1 will give backup. So for that fault current R1, same plug setting 125%. TMS 0.1 I can't change. And that 0.25 second has to be maintained. If not, then R1 0.1 is wrong. I will have to take R1 0.15. If I take R1 0.15, then R4 will also change. So like that, there will be iterations, many iterations. Fortunately, my dear friends, here, you are lucky. You are lucky that this video will go for about 45 minutes. Otherwise, this video would go for 24 hours. If at all you are not lucky. But my dear friends, you are lucky. You are lucky that the exercise is yet not complete. We have to think of fault at F2. The fault current 5539, you can check up the table. Would you like to see once again, so that you don't say that मैं कुछ असल पसल कर देता हूँ. 5539 and 1910. So 5539 I will go with 5539 plug setting of R4 125% is 11.078 and 3 upon log PSM into 0.1. I have already found out 0.2872. PSM of R1 1910. Fault current is different, but fault location is same, F2. Right? And 1500 is CT ratio. Plug setting multiplier is 2.55. Top of R1, I am not changing anything. Plug setting and TMS also 0.1, I am not changing. I am getting 0.7379. I am finding out the difference, 0.7379 and 0.2872. Difference is 0.4507, which is more than 0.25. So my exercise is over just in one iteration. Lucky, my dear friends. Very lucky. Very lucky. One has to check that for fault F2, R1 backs up R4 with these settings calculated, which my friends we have done, and therefore now our exercise is fully complete. Our exercise is fully complete, right? So plug setting and time multiplier settings I have found out, right? I have not to go for the second iteration, and therefore I can summarize now. Ground relays I will keep aside because that will be another tutorial class. Plug setting of R1, R2 125%, R3, R4 125%. Time multiplier setting of all four relays is 0.1. And with all the possibilities, one line contingencies, worst normal rated current flowing in case of contingencies, worst fault current flowing in case of contingencies. I have found out that this is the best and optimum setting that I can find out. To find out the optimum relay setting in an interconnected system is a very cumbersome exercise. My friends, if you have understood very well, if you have not understood, my phone number is there. Anyone who wants to note down my phone number, I am slowly speaking. +91 India 9723456236. I repeat, +91 9723456236. That is my phone number. I am available on that phone number on WhatsApp. I am available on normal text message. I am available on that number on Telegram. Right? And I have got another number, 9791 India 97241 53763. I repeat, 97241 53763. On that, I'm available on WhatsApp and Signal too. Right? Calling, my friends, WhatsApp calling is free. And if you want to call a normal calling, you will be charged, because the people will charge you. I will not charge, people will charge you, but you are most welcome. My email ID is ozabhuvanesh@gmail.com. I repeat, all second letters, OZABHUVANESH. I repeat, Oza, that is OZA Bhuvanesh, BHUVANESH @gmail.com. You are most welcome to ask any questions. I am not Vyapari. I am not a businessman. I am a teacher. I want to share my knowledge. So through these YouTube videos, I am sharing knowledge free of cost. Personal teaching also, no doubt, based on availability of time, based on mutual convenience. We can talk and we can discuss. But this way, we finish this tutorial class. Little difficult, my dear friend, I do understand. Little difficult. I wanted to enter into this difficult session. And if you want to understand power system protection, remember this name. Remember this name, which will teach you power system protection. Many people, I do not want to name them, because naming in such a social media platform is not good. But people from Malaysia, people from Pakistan, people from Oman, many people from India, and there are about 2000 loving students of mine. They all know this name. So note down this name in your brain. कागज पर लिखना हो तो लिख दो. Adopt me. Your education will be made up. Let me apprise my education. Adopt me. Remember this word, adopt me. Stay tuned with adopt me. Remain with me. I'm going to be with you for coming 150 YouTube videos. Thank you, my friends. Good day. Right now, right to say good night to everybody. Very good night. Sweet dreams. Thank you.